Welcome back, everyone, to another edition of The Explainer. I'm genuinely so thrilled you're here because today we're tackling something that is absolutely foundational. We spend so much time talking about the magic of the internet, right? The apps, the software, the cloud. But today, we're stripping all of that away. We're going straight down to the absolute bottom layer of network communication, the physical layer. If you've ever wanted to understand how all this digital wizardry actually happens out there in the real world, well, you're in exactly the right place.
Now, I want you to just think about this question for a second. How does digital data, which is, let's face it, completely abstract, just invisible code and software, how does it actually become a physical reality that travels across a room or, across an entire ocean? We are so incredibly used to the magic of Wi-Fi and instant messaging that we kind of just completely forget about the tangible physical realities of data transmission. But the truth is, every single cat video, every critical email, every video call, it literally has to turn into physical energy at some point. And that's exactly what we're going to demystify today.
Okay, let's dive right into this. Here's our quick roadmap for today's explainer. We're going to start by looking at connecting to the network. Then we'll review the hardware and standards. From there, we'll get into encoding and signaling, figure out what bandwidth actually means, and finally, we'll look at the physical highways themselves with copper cabling solutions.
All right, Section 1, Connecting to the Network, the physical connection.
So, before any of this network communication can even happen, a physical connection to a local network absolutely must be established. No exceptions. Whether you're using a wired connection plugged straight into the wall or a wireless setup relying on radio waves, you need a physical gateway. And that gateway is your network interface card, or NIC. To kind of see where this physical layer sits in the grand scheme of things, we just look at the encapsulation process. Data moves down from the user application, it gets wrapped up in TCP segments, then IP packets, and finally it becomes an Ethernet frame. And the physical layer? It's the absolute final stage of this journey inside your device. Its entire job is to accept that complete frame from the data link layer and prepare it for the outside world. It's literally the last stop on the train before your data leaves the station and heads out onto the local media.
Moving on to Section 2, Hardware and Standards, the rules of the physical realm.
To make sure data from a smartphone can actually talk to a server halfway across the world, we need rules. And when we compare the different network layers, a pretty stark difference emerges. Up on the top layers, you've got your TCP/IP standards. Now, those are implemented entirely in software, and they're governed by the IETF, the Internet Engineering Task Force. But down here at the physical layer, we are dealing with real, tangible hardware. We're talking devices, media, actual connectors. You can't just write a quick software patch to change how a copper wire conducts electricity, right? Because of that, physical layer standards are governed by completely different organizations, groups like the ISO, ANSI, and the IEEE. They have to rigorously define exactly how the hardware is built so that a cable manufactured in one country fits perfectly, and I mean perfectly, into a router manufactured in another.
Which brings us to Section 3, Encoding and Signaling, the translation. So this brings us to the actual translation phase, where the physical layer really does its core job. How do we take those abstract digital ones and zeros and transform them into physical, measurable energy? Well, we use a process called encoding. For instance, using Manchester encoding, a stream of bits, those ones and zeros, is converted into a format the next device can actually recognize. By dropping or raising the electrical voltage at very specific times, this coding creates completely predictable, readable patterns. So the receiving device just reads these voltage changes and instantly knows, okay, a voltage drop in the middle of the cycle? That's a 0. A voltage rise? That's a 1. It is literally translating math into electricity, which is just brilliant when you think about it. And this brilliantly illustrates what happens next, which is signaling. Once we have our encoded pattern, it has to actually be pushed across the physical medium. A digital signal can be translated into AM, FM, or PM, physical microwave waves for wireless transmission. So the signaling method changes entirely depending on what medium you're actually using. Like if you're using copper cable, you use electrical signals. If you're on a fiber optic cable, you're literally firing pulses of light. And if you're on Wi-Fi, you're modulating microwave signals just like the waveforms we see here.
All right, Section 4, Understanding Bandwidth, the speed limit.
So now that we've got this physical energy flowing, whether it's electricity or light or microwaves, how do we actually measure it? Well, bandwidth is simply the capacity at which a medium can carry data in a given amount of time. It all starts with the fundamental unit, bits per second, or BPS. From there, we scale all the way up. We go to kilobits, megabits, gigabits, all the way up to terabits per second. And to put that into perspective, a terabit is a mind-boggling 1 trillion bits per second. But remember, these numbers aren't just arbitrary goals. The bandwidth you actually get is strictly dictated by the properties of the physical media you're using, our current technological limits, and, well, the literal laws of physics.
Now, an absolutely crucial point here is making sure we don't confuse our terminology, because it is super easy to get lost in the jargon. Let's quickly clarify these three terms. Latency is the delay, basically the amount of time it takes data to travel from point A to point B. Throughput is the actual measure of the bits transferred across the media over a given period of time. But honestly, my favorite term here is goodput. Goodput is the actual usable data you get after you subtract the traffic overhead from your throughput. It's the stuff you actually care about, like the loaded web page or the streaming video, minus all the necessary but totally invisible formatting data that helped it get there in the first place.
Finally, Section 5, Copper Cabling Solutions, the medium.
To wrap up our explainer today, let's shift our focus downward to the actual physical highways carrying these signals. Because despite all of our amazing wireless advancements, copper cabling remains incredibly common, inexpensive, and super easy to install. But because copper relies on electrical signals, it has some natural enemies. First up is attenuation. Basically, the longer the electrical signal travels down the wire, the weaker it gets. That's exactly why cables have strict length limits. Then we have outside interference from EMI and RFI, which can completely distort the signal. And finally, there's crosstalk. That's what happens when the electrical signals from two adjacent wires bleed over and interfere with each other. If you've ever been on an old landline phone call and faintly heard someone else's conversation in the background, yeah, you've experienced crosstalk.
So how do we fight this? Well, with unshielded twisted pair, or UTP cable. This is the most common networking media in the entire world. But notice how the internal color-coded wires aren't just running straight side by side. They are deliberately twisted together. It turns out, the physical act of twisting these opposing circuit pairs together actually cancels out the magnetic fields and beautifully mitigates that exact crosstalk interference we just talked about. It's a remarkably simple but effective trick.
Now, what's really interesting here is comparing standard UTP directly with shielded twisted pair, or STP. You see, if you're running cables in an environment with a lot of heavy machinery or intense electrical interference, just twisting the wires isn't going to cut it. So STP adds a braided metallic or foil shield just beneath the outer jacket, and sometimes it even puts foil around each individual twisted pair. This provides absolutely superior EMI and RFI protection. But as you might guess, it does make the cable a lot more expensive and significantly stiffer, so it's harder to install. And that brings us to the end of our journey down to the bottom layer of the network. You know, the next time you connect to a wireless network, I really want you to remember that your data is only truly wireless for a very short jump to the nearest router. Beneath every single abstract software action, every click, every swipe, every download, lies a vast, tangible physical infrastructure of copper highways and fiber optic pulses. So I'll leave you with this final question to ponder. What physical medium is powering your digital life right now? Thank you so much for joining me for this explainer. Keep learning, stay curious, and I'll catch you next time.